Hello, my name is Safa Kamran and I'm a master's student in Aalto University. My master's is in geoinformatics and today I'm going to present my master's thesis and the supervisor was Assistant Professor Henrikki. The topic of my thesis is predicting CO2 emissions of private transport in Helsinki region using transfer learning. Contents. The contents of my thesis are objectives and research questions, literature review highlights, methodology overview, key results, and discussions and conclusions. Objective and research questions. Objectives. Develop a predictive pipeline for urban CO2 emission using machine learning. Train models on Espoo data and then apply them to Helsinki using transfer learning. Identify key spatial and behavior drivers of private transport emissions. Evaluate model accuracy and generalizability using H3 hexagon grids. And for the research questions were how accurately can Espoo train models predict private transport CO2 emission in Helsinki? Which machine learning models like random forest, HistGradientBoosting, or linear regression perform best in this scenario? What are the most influencing predictors of emissions at the H3 hexagon level in Helsinki? Now, let's start with literature review highlights. Firstly, like urban CO2 emission and transport. Urban transport remains a major source of greenhouse gas emissions, especially in car dependent cities like Helsinki and Espoo, and it is like worldwidely a very important topic. Despite sustainability effects, lower density areas still exhibit high private vehicles emissions. Then modeling approaches like traditional top-bottom models lack spatial granularity, while bottom-up models like VTTs offer higher local accuracy but require intensive data. So machine learning model, especially random forest and gradient boosting, handles non-linearities better and improves spatial prediction accuracy. Spatial units H3 hexagon. H3 grids provide uniform spatial units that minimize boundary biasness and improve the interpretability of emission patterns. Then transfer learning in urban mobility. Transfer learning enables predictive model trained on in data-rich cities to be applied in data sparse one when cities share structural similarities like that of Helsinki and Espoo. Model transfer can be both feasible and effective. Now, let's go through methodology overview. Approach. Transfer learning was applied by training machine learning models that we discussed before as well, like we will use linear regression, random forest, and gradient boosting, and testing them on Helsinki region using uniform H3 hexagons. For the data, we used mobility locomizer OD pairs having CO2 emissions, distance, and time. For built environment statistic Finland grid data, here we get the population data and stuff like that. And for transport network like HSL, GTFS, from there we get the stop, signals, average speed, etc. And for the evaluation, we use matrices like R2, MSC, MAE. And validation, applied models to Helsinki without retraining, interpretations, feature importance, and tree models. Now you can see that how data workflow and feature engineering pipeline work like in this image, like map trip origin destination pairs like OD pairs and then we see like population and built up area locomizer OD trips data, and then we feed it to speed stop traffic signal etc, and then we aggregate trip data to hexagons, then we merge and doing stuff like, and then we assign municipalities to hexagons like these belongs to Espoo and these belongs to Helsinki, that like we define the proper boundary etc, and then final hexagon feature table was generated. And then we have another figure as well showing of model training and validation pipelines. Firstly, what we did was we have the Espoo hexagon feature table with CO2 ground truth values. And then we train and test split in Espoo hexagons, and then hyperparameters tuning cross validations etc. And then there was a model training like linear regression, radiant boosting, and random forest, and then validate on held on Espoo hexagons, and then we train model, and then we predict on hexagon Helsinki hexagon axis. Helsinki hexagon feature table was made, and then we predicted CO2 for Helsinki region. Now, for the key results, model performance on Helsinki data. Its linear regression, like R square value, was like around 0.991. For random forest, it was like around 0.98. And for his gradient boosting, it was around 0.96. Like all models showed high predictive accuracy, with linear model slightly outperforming others in specific transfer training, as it was very simple one. And now we'll discuss top predictors of emissions: total car distance, shortest path distance, trip frequency, built environment variables like pollution and built up area, which has a bit of low influence. Now, spatial insights. Most accurate prediction in suburban areas, high prediction error in dense central Helsinki. Conclusion: transfer learning using Espoo data is highly effective for predicting CO2 emission in Helsinki, especially with ensemble models. Now, there are the two tables which are showing model performance metrics for CO2 prediction in Helsinki. Firstly, we'll see the first table. There we can see there are three models which we used and discussed earlier as well: linear regression, random forest, and gradient boosting. And the test size of all three was the same. And for R square value for linear regression, we find 0.991. For random for it was around 0.98, and for gradient boosting it was around 0.96, which was very good of all three models. And what features we used were total car distance by time, shortest distance by time, and then by shortest distance by length, total car time, average speed, stop count, traffic signals, built area, number of trips, population. And for the linear regression and for all other models like random forest, gradient boosting, we see the total car distance and total shortest distance was the most influencing factors, and other were effective like a very bit like low effectiveness was there. Now, this is the scatter plot of observed versus predicted CO2 emissions per H3 hexagon in Helsinki using all three models. Like firstly, it is of random forest. We can see that how values was trained like predicted Helsinki hexagon train set, and then true Helsinki hexagon values. And then similarly, we performed it for linear regression and then for gradient boosting, and you can see all three maps here. Now, key results, like now we will see that variable importance plot like random forest, gradient boosting, linear regression, which model is performing best. Firstly, let's start with the random forest. Random forest, like total car distance affected it most, and then total shortest distance as well, and it all other variables were also influencing it. Like we can see population was also having the effect, like a bit of low, but still total car time was, so number of trips, average speed, total built up area, and stop count and traffic is not affecting that much. But if we go to the gradient boosting, total car distance and total shortest distances are affecting it, and number of trips and population was affecting more here in gradient boosting, and all other factors like total car time, average speed, stop count, traffic signals, built up area was not affecting that much. And then we will go like to the simple one like linear regression. In linear regression, it showed that like total car distance was affecting too much, and then number of trips other than that like shorter distance was also affected, but it was a bit low, and the total car time was also low, but it has no effect on population, total built up area, traffic signals, stop count, average speed, etc. Because it is like simple model, so it didn't cater much of the other things. Now we have the spatial patterns of prediction. What we did was observe CO2 per hexagon. You can see first image A1, and then B1 was predicted CO2 per hexagon, and then lastly was differences between prediction minus observed value, and you can see it. Now let's go to discussions and conclusions. Key insights. Transfer learning from Espoo to Helsinki is effective. Like we already saw that it was achieving high R2 value even without retraining. Like it was showing like around 0.96, like above 0.96 of all three models. Assemble models like random forest and gradient boosting capture spatial and behavior complexity better than linear model. I think so. Like random forest performed very well among linear models and gradient boosting. And then emissions are driven primarily by trip distance and frequency, not static features like population built up area. Like it, firstly, when we see the graph, it showed us clearly that trip distance and frequency was like affecting it very much, but static features like population, what is the population of each grid, each hexagon, and what was the built up area on it. It was not affecting that much, even it was showing in some of the models negative effects. Now, for the conclusion, we defined machine learning models such as linear regression, gradient boosting, and random forest, and trained in data cities. For example, of like for my case, I used Espoo, and then transferred to data scared areas, which was in my case was Helsinki, for accurate fine scale CO2 emission prediction. And my study shows that it results was really good, and that in future we can go through like transfer it to other cities as well, like for Tampere or in Finland or worldwide. This study provides a scalable approach for urban climate planning and support evidence-based transport policy. In future, we can like use other we can remove other features and just go to the simple one and see if these are the enough one or not. But still till now I did this one things, and these are some of the references which I used in my thesis and this presentation as well. You can go through them as well. And thank you so much. This was the presentation, and if you have any question you can ask me or mail me. And yes, so I hope you like my presentation, and if there's anything you can ask me. And this is what I worked for my master thesis. And yes, thank you so much.